Now let's quickly recollect what happened in the previous lecture. Okay, so we defined perfect secrecy and just mentioned that many notions they are equivalent, and ciphertext only attack, we discussed the definition of that. Again, security against only one ciphertext where the attacker is computationally bounded, and then we talked about the formal definition of perfect secrecy, and then we discussed one-time pad, which is just just assume the message space, key space, and plain text space, they're all n-bit strings. Your encryption is as easy as just XORing the message string and the key string. And decryption is it's just exactly the same operation again, ciphertext XORed with key. And then we were stuck at the proof. So now let us quickly finish it off. Okay, cool. So now, okay, for one-time pad, we want to show that probability that the adversary will learn something about in the view of adversary, the probability distribution of M given the ciphertext is C. We want to prove it whether it is same as the a priori information the adversary has. Means this conditional probability does not change. So now, okay, so we started with left hand side, and so this you can always write it as correct? This is the definition of conditional probability, right? This we discussed is nothing but probability of K, because your ciphertext C is M XOR K. Given C and M, this implies C XOR M equal to the key, right? So if this message has to result in this ciphertext, it can only happen for one key. And what is the probability this is going to happen is same as the probability you are going to pick up the key, right? Because only for that key this event is going to happen. So this is nothing but we know that it's probability of K, but probability of K is it's 1 over the size of the set K, which is nothing but okay, I will just write it as the key space into divided by probability of C. Now, so we were stuck there, right? So now any ideas how to progress? Did anyone get a chance to think? Vivek.
The probability of K is 2 to the power.
Probability of K is fine, that is fine, 2 power n, we know that. But then how to proceed? We want to get back here, right? So then probably let's not take this approach. Let's look it in a different way. So probability of M intersection C, I can always view, probability of M intersection C is same as probability of C intersection M, right? Set intersection is commutative, right? So if I write it like this, this is the same, right? These are all the same. Now, but I can also write it as probability of C equal to C given M equal to M, right? Into probability of M equal to M. Same thing, right? So this can also be used probability C equal to C given M equal to M, right? Same thing, right? This is the conditional. Here you are assuming that probability of M equal to m is not 0. If it is 0, then just reduce the message space accordingly, then everything will take care. So I will just assume probability of m equal to m not equal to 0, and this is without loss of any generality. So now you already got m equal to m. Ultimately, we want to go there, right? From here to here, we got it. So now we have probability of C. So what is interesting is, now given the ciphertext, the probability of the message capital M, the random variable m being equal to small m, we want to show it is independent of the ciphertext. But it also turns out that this probability that of getting a particular ciphertext for given a particular message is also independent, because ultimately if whole thing has to be equal to this obviously is going to cancel and this has to become 1, right? This means this equal to this. So probability of getting a ciphertext is actually independent of what the message was encrypted. So now how do you prove it? No ideas? Okay, so that's actually easy, like probability of C getting a ciphertext, I can always write it as the total, the total probability rule. It's just that probability of, I think, okay, I should have written probability of C equal to C. Hope you understand by that. I have written this probability C, so maybe I think I'll erase this. So probability C equal to C, I can always write it as sum of conditional probabilities, right? So probability C equal to C given m equal to m into probability m equal to m, right? This I can always write. Obvious, right? So this is nothing but probability C equal to C is what is the probability? This is nothing but probability of C intersection m, right? So what was the probability that you got the ciphertext with respect to one particular message? And because they are all mutually exclusive events, I just need to sum over it. So this is a well-known formula, and it's very intuitive. And this, for the same reason, like this is independent, right? Because same reason, What was the probability you got this ciphertext for this message is just a probability of choosing a key, and it is 1 over 2 power L, right? 1 divided by the key space. So this one is independent, and I can always say, let's mark, so this is nothing but 1 over 2 power n. And I can always take it out, and sum of the probability of the messages is unity, right? So you got it as 1 over 2 power n. But what was this probability? This is also 1 by 2 power n, this is 1 by 2 power n. So these are equal, and you get back this. So it's proved easy. I mean, it's simple application. So to solve the assignments, one trick what you can surely use is the fact that we have chosen those problems means if you are attentively listen to the lecture, then that's the hint that you should be able to solve it. When you are working on research problems, this is not necessarily true, right? You don't know. I mean, few times you may not know whether it's solvable or not. But now, because it's part of your problem set, you can be sure that there exists solution. Okay, so let me move on. So fine, we saw the proof and the practical limitation of one-time Paddy's key space should be as large as the plain text page, which is not good.
So actually, is it vulnerable to brute force one-time Paddy? is or message is very
No. It is
suppose
no.
we have 4-bit string, then
Sorry.
if we have 4-bit message,
Again, okay, fine. You can exhaust over all the keys. No, but how can you exhaust over all? Yeah, you can exhaust over all the keys. Fine. We proved the security against computationally unbounded adversary, right? So it can do any brute force, but it will not change the probability distribution. So if you take a randomly, even don't take the 4-bit case, just take the 1-bit case. 1 bit, you pick up a random key, encrypt, and ciphertext is 1 bit. Just looking at the ciphertext, still from the adversary point of view, this is unconditionally probability half. Underlying message, whatever happens, even in the 1-bit case. So we saw the military application, right? 0 could mean don't attack, 1 can mean. So still it will not be able to, know anything. Good. So then we discussed computational security, where basically we make some assumptions and we'll reuse the key, right? And then yeah, but these things can be broken against a computationally unbounded adversary. We just assume the adversary is efficient, namely it runs in probabilistic polynomial time. So then we discussed pseudo-randomness, pseudo-random generators, and saw the mathematical formulation. Basically, if adversary is given a string sampled from a uniform distribution or the pseudo-random distribution, it should not be able to tell anything. We actually saw a counter example, not an example. Then we believe PRGs exist, no proof yet, but stream ciphers are a good practical instantiation of it. Then we constructed a ciphertext only attack from a PRG, where we just XOR the message with a pseudo-random string, not the truly random string. And then we discovered what is PRFs, pseudo-random functions. Again, we just believe it to be secure, believe it exists, and we can get a fixed length CPS or encryption scheme. So probably I made a mistake here of that, not for multiple messages. Of course, if it is secure against chosen plaintext attack, it can get ciphertext of any number of messages. Because it's efficient, it cannot get infinitely many messages. Of course, it's just polynomially number of messages. And then, but it's only a fixed length. You cannot use it for messages of longer length. But you have constructions from PRF to get a multi-length CPS or encryption scheme. And block ciphers are the good practical instantiation of PRFs. And then we looked at MAC. So here on input a message and a key, a tag is generated. Tag is sent along with the message in the clear, and verify, accept or not. And we discussed chosen message attack and strong chosen message attack, and then yeah, we constructed a fixed length. Again, it can encrypt multiple messages, but it's only again fixed. It cannot encrypt multiple length messages. It's just only a fixed length message it can encrypt. But again, there are constructions that can handle variable length messages. But yeah, we don't have time to see that. Good. So now, okay. So now let's go to hash function. Probably I remember. Maybe it's not a bad idea to solve just one more problem. Do you remember anything from the problem set 1? Any question you find it particularly difficult? So what do you which question you think is quite more difficult? Okay, then I'll myself ask. Okay, so now we saw that, you just assume that, for a perfectly secure encryption scheme, your key space should be as large as the message space. Now what the question says is, but we remember, if we encrypt a message with respect to a given key and then decrypt, we should always get back the message, right? Suppose you relax that. Okay, well, I can tolerate some errors in decryption, namely, I may not be able to recover the message, but with some probability, I may not be able to recover the message with probability 1, but even if it with some probability, say 1/2, 1/4, or 1/8, still can I construct a perfectly secure encryption scheme using a key space smaller than the message space? Say for example, okay, so any guess whether it can be done or not? How many say yes? How many say no? Wow, it's 100% can't say. Okay, great. So yeah, being humble is it's the first step of being a good researcher. Okay, so we only know of one-time encryption scheme, right? So let's try to construct an example. Suppose your message space is 1, and then your key space is 0, 1, L, where L is less than N. So according to the perfect secrecy definition, this cannot be the original. This cannot be a perfectly secure encryption scheme. According to the definition we have, you can assume that. We have not proven it. You can assume. But then now I'll give you a construction. Again, we only know one-time pad, right? So based on that, I'm going to give a construction. So your message, what you do is first you have the n bit message, right? First truncate it to L bits. So what I just mean by this notation is M truncated to L bits. So if M is say 10 and K is 9, so first truncate the message to say 9 bits, some 9 bits. Need not be first 9 or any 9 bits. So then now you XOR it with the key. Okay. And we know intuitively, so this is nothing but one-time pad, right? So you shrunk the message space. So the set M becomes smaller, M prime. So the cardinality was 2 power N, it became 2 power L. And then now you are applying one-time pad on this, which we know is perfectly secure. But then the decryption is a problem because you are not sending the remaining N minus L bits. You are only taking the L bits. So you left out remaining L bits, and it goes to the receiver. So receiver now does the same thing. C ciphertext K will give you only the L bit message, right? Because you have not sent the remaining L bits. And now, how can it recover the message, the remaining N minus L bits? Any idea how it can recover? Again, we cannot recover it with probability 1. So just guess the remaining N minus L bits. And what is the success rate? Is just 1 over 2 per N minus L, right? So you say you have N 10 bits, L 9 bits. So you encrypt, say, for the first 9 bits, send it. So it will get the 9 bits in clear. So it just needs to guess. So the probability the decryption is going to work is half. But if it is okay for its application, then so you have a perfectly secret encryption scheme which has a key space less than the message space. But now you cannot decrypt it with probability 1. Yeah, looks a complicated problem, but turns out to be quite easy in the end. So suggest you go back and try as many problems as you can. Good. Fine. This is all good. So now, yes.
Actually, as we do in log cipher, if we repeat, we have to show that it is secure, right?
I'm sorry.
As we do in log cipher, after the after we take the 9 bits, again we XOR. If we repeat it with the same key.
Oh no. This is again secure against only ciphertext, only one ciphertext attack. The attack model is same conditions as the original definition. Namely, the adversary will only see the ciphertext, only one ciphertext. If you encrypt with the same key, more than one message, then no, it will not be secure. Need not be secure. Fine, good. So then now let's move on to hash functions. So hash functions, first I'll tell you that they have a lot of applications in data compression and then message integrity and authentication. So what's a hash function? Informally, it's just take a set of all binary strings of I mean any length. So this includes the null string, and like give any number, it would include all the bit strings of that size, and it's going to compress. I mean compress means it's just a mapping to a finite space. Say let's call it L bits. There is a reason why it's L is a function of n, but don't worry about that. So this is a finite space. Only 2 power L possibilities are there. So this function, can it be injective? Huh? Can it be injective? Can it be one-to-one?
No.
Why?
Because both side doesn't have equal number of. You can have a 1-1 mapping.
Why?
Both side is not balanced. Like,
What do you mean by balanced?
like right side we have a limited number of elements, on left side.
Oh, okay. Actually, this tempts me to ask. Suppose you take the set of integers. What is this? Oh, I cannot write on this, right? Yeah. Okay, no worries. I just take the set of integers and take the set of natural numbers, say starting with 0, 1, 2, 3. So all non-negative integers. So this looks like a smaller set, right? Can you have an injective function? Huh? Can you have an injective function?
Actually, here it is infinite. So
No, can you have an injective one-to-one function from set of all integers to set of only non-negative integers? No? Yeah, then I think you should go and read some set theory. You can have it, but here from infinite set to finite set, you cannot have it. Sorry?
according to pigeonhole principle, it won't.
Yeah, okay, pigeonhole will answer. That's the answer. What looks intuitive, maybe it's not a bad idea to sit down and work out details. You know that map, right? Okay, can you give me an injective map from Z to N?
0 maps to 1.
Sorry?
0 maps to 0 maps to 1. Then
Yeah, exactly. So 0 maps to 1. Now you to go alternately. 1 maps to 2 and -1 maps to 3, and then 2 maps to 4. So just go on incrementing, shifting. So because these are infinite sets, you can still find a map. So though it looks smaller, you can still have one-to-one because you're dealing with infinite sets. But here, as he said, it's a pigeonhole principle. You can always finitely assign this many, and then, but in that case, pigeonhole principle is not going to end because this set is also infinite. You can always go on assigning. So good. So then, of course, there will be, so because it's not one-to-one, there will exist collisions, right? They will exist. But now, again, we are always working with computational security, right? Our adversaries are not like infinitely powerful. They don't have infinite computation power. So for an efficient adversary means it runs in polynomial time, whatever that means. So again, when you say polynomial time, you should give the input size, right? So that's why I wrote it as a function of the input size. But don't worry about that. So if it, for a computationally bounded adversary, it should not be able to find two distinct strings that map, that hash to the same value. So then such hash functions are called collision resistant. This is formally done. Again, this does not mean it's injective, wrong. It's just for a computational adversary in a finite time, or not in a finite time, in a limited amount of time, you cannot find a collision. So there are other security notions. So this is called a weak collision resistance. What we saw as collision resistance is actually strong collision resistance. Now what we are seeing is weak collision resistance. This is another notion of security for a hash function. It's called a second preimage or target collision resistance. So here what you do, you first randomly pick up a message as a string X. Again, you should be very, very careful, with these terms when you are making it more precise. From an infinite set, picking up something at random, does it make any sense? Doesn't make any sense. How can you have a uniform random distribution? So what actually formally it means is, first restrict your attention to some n-bit strings. N can be anything. So now, if you look at the subdomain of all n-bit strings and then look at the map, so then the security definition makes sense. And that's why I said the size is L of n, because you need to fix the input size when you are analyzing the security, Otherwise, the hash function, it can compress, arbitrarily long messages. It's fine. So pick up a random n-bit string, compute the hash. Computing hash should be very efficient again. So, but then you cannot find another string, a different string, maybe of the same size. Then which hashes on to the same value. So this is different from collision resistance. Why? There in collision resistance, you need to find some two distinct strings where X need not be uniformly randomly picked. It can be anything. It should hash to the same. But here you are imposing that the first X, it has to be randomly picked. Turns out that the strong collision resistance, as the name suggests, implies weak collision resistance. Proof is homework. Again, some hint is do it by contradiction. Assume this does not imply, so then just prove the counterpositive. But it turns out that the second pre-image resistance, that is weak collision resistance, is not equivalent to strong collision resistance. I cannot get into the details, we are really short of time. So there is another notion called one-way property. It's the pre-image resistance, it's a bit confusing, second pre-image. So what does this one-way property means is, if you pick up a uniform random element from this, it should be infeasible to find an X such that it's infeasible to find the pre-image. First of all, we have to be, again, pretty, first of all, okay, you have an infinite set, you have a finite set. Will any function be surjective onto? Will any function be onto? Will every element of this, should it necessarily map? If you have a function from an infinite set, this set of all strings to a set of set of strings of finite length, actually of L-bit length, should every function map? Should the range be the whole set? Why? Give me an example. Brilliant. All mapping to the zero string, So it's clearly not a surjective map. It's not an onto map. Okay. So assume, let's exist. You pick up a random by. You can assume that So basically, if you make it precise, it means that if such an X exists, pick up a random Y. There might be a pre-image or not. Don't worry about it. If there is a pre-image, you should be able to find it out. So this is called a one-way property. Hash functions easy to compute one way. Given X, you can compute h of X, but you cannot invert. Actually, it turns out. So does the one-way property, that is pre-image resistance, imply the weak collision resistance? Well, intuitively it should be true. Yeah, because if the function is hard to invert for a random Y, then same should be the case to invert h of X for a random X. Because you pick up a random X, compute h of X, right? Call it Y. So now question is, can you come up with a distinct X prime such that Y is h of X prime? Actually, no, that's not the case. Again, homework, try to do it. So you can just accept this fact for now. If you have a hash function, so then collision resistance is like the strongest property, strong collision resistance. That is going to imply everything, no? It's going to imply one wayness, it's going to imply weak collision resistance. In fact, weak collision resistance will imply one way ness, but not the other way around. And probably this, why am I mentioning these notions is this might come up in the invited talk, might come up. So then, so just so that you at least you're familiar with the term. So and different, it's not just you use the strongest security notion. Again, depends on the application. Different applications require different security notions. And Unix passwords, they are stored as hash of the password. Is it just stored as a hash? Why?
Because one can have an input table and map it.
Good. So it's not a good idea, to store the passwords in the clear, because if the hard disk is lost, then it's a bad thing. So store the hash. But again, if you just store the hash, then again it's always prone to so the adversary can exhaust many, try out many passwords, hash it. Hash function, the algorithm is always public, right? That's the Kirchhoff's principle. So just it's not a good idea to just hash the password, right? And then, so what usually some randomness is added to that. Probably the day you created your account, so many other information plus some randomness. They are all concatenated to your password, and then it need not even be concatenated. All this information, they are suitably mixed together, and then they are hashed. So that's called salt. A salt is usually, if you come across the phrase salt is added to your password and then hash, that's what it means. And again, it's always easy to store small strings of smaller size than along the strings. That's the data compression is one of the utilities of most important utilities of hash functions. So yeah, then again it's a homework. It requires both pre-image and second pre-image resistance. So you'll get too many homeworks today, in addition to the third problem sheet. Those who came late, maybe, did you get everyone get a copy of this? So I can just pass around. Just pass around. Good. And of course, some applications. Why pre-image resistance is useful is that's one-wayness. One should not be able to learn the actual bit by looking at the hash. If it satisfies the one-way property, then looking at the image, the hash, we should not be able to figure anything about the domain. And again, if you want a malicious bidder should not be able to change the bid which matches the original committed bid. Suppose you commit to some value, hash it and give it. Later, say suppose you commit in an option, say to $1 million. So then later you don't want to change it to say $1 and then come up with a hash, right? Only hash, assume only hash is made public. So you should not be able to change it to $1 and then get the same hash value and claim that. So we need, in those cases, we need the strong collision resistance. So there are, again, we don't have a provably secure hash function, but then there are very good, very efficient practical constructions. MD5, well-known example, designed in '91, but now it's completely broken. And NIST, there's a standardization agency called NIST, National Institutes of Standards and Technology. Sure? Sorry, I don't remember that. So NIST had arranged a competition, and two candidates were chosen. Now they are called SHA-1, means Secure Hash Algorithm 1 and 2. It's derived from a block cipher. And then, like a couple of years ago, they called another a competition to select a candidate for SHA-3. That's secure hash algorithm, that number 3. So then, yeah. So one of the candidates called Keccak, it won, it became the standard. So now Keccak is SHA-3, standardized as SHA-3. Again, I will not, no time to get into details, just wanted to mention the names of the practically used hash functions. So let's quickly look at some applications of hash functions. Suppose it's used in what is called fingerprinting and deduplication. So now you have a file, big file, maybe running into few megabytes or maybe even gigabytes. So now you just want to, so you create what is called a message digest. Many would be familiar with that. So you just hash that, and that serves as a unique identifier. And this idea has many applications. Integrity check, you know. Suppose when you download a file, next to that you see a checksum, they call it a checksum. So it's a very short string, you know, relatively short, much shorter than your original file. So when you download I don't know, for pirated movies also probably if you download, they might put, I am not sure about that, but when you say, you download an operating system, for instance Ubuntu, you know, you would surely see the checksum. Of course, nothing prevents anyone to put a checksum even for a pirated movie, you know. So when you first download a file, what's the guarantee that you received the file in its full form? You know, there could be, you know, errors during the communication. Of course, you have all the network layers, right? Physical layer up to application layer. You know, they will take care of it. But again, if you are worried about the security aspects, so then man-in-the-middle attacks, for instance. So then, you know, download it, run the hash algorithm, which is public, for instance, SHA-3, and then, you know, compute the digest, message digest, and it should match, you know, what is claimed on the website. So in the process of downloading, if someone in the middle, you know, manipulates it, then still you can catch it. Again, the security properties of the hash function, they will. So collision resistance is going to imply that, right? If the adversary in the middle changes your data, so then you get two different messages and hashing to the same, that cannot happen. If you can find one collision for SHA-3, remember you are going to become very famous. So and then virus fingerprinting. So usually virus scanners, they store hash of the known viruses. So when you get an email attachment or an application download, so virus scanners compute the hash of it and then compare it with the hash the list of hashes it already has. Why it wants to store the hash?
Because normally virus change the content. So whatever code in the virus will be changed.
No. Again, the virus could change the. See, we want message integrity, right? Someone in the middle can change anything. Why? Okay, even in the file integrity check, why you computed a hash, not you know, check everything bit by bit. They can always publish the whole. They can always publish, right? Each, like if it is 1 megabyte, you can on the server when you download a file, it can always have a 1 megabyte file saying what is the ith bit, right? It can always do that. But why you want to hash it? It's shorter. That's the whole point. It is short. It's easy to put a 256-bit string, you know, 256-bit string. If you use 8 bits to encode one, I don't know how many. For an English character, you need 5 bits, right? Whatever, in a standard encoding. You don't need how many bytes? You don't need many bytes. 16 bytes will be enough. Good. So, yeah. Remember, hash function always compresses. And deduplication, you know, when, again, if you want to upload a movie, you know, you download a pirated copy of a movie, you want to upload it, say, in Dropbox. Many people, of course, Dropbox has policies, you know, says you cannot do that. But suppose you somehow bypass that and convince Dropbox that you are uploading some video of your own. You know, two people if try to upload, then always say Dropbox tries to maximize its resources, right? why it wants to keep, if it knows that there are two identical copies, it's going to save its space on its in its storage servers. It doesn't want to duplicate the files, right? So what, for every file, it's going to put a hash. If someone uploads another file, it's going to compute hash because they are long, they are short. It's going to quickly check it. That's easy. So then it avoids, So the other user, of course, so it's going to it's going to put a pointer to the only one copy of the file it would store. So hence it can maximize its resources. This is called the technique of avoiding deduplication. So again, another cool application of hash function. Again, now another application is password hashing. So you send a password. Usually passwords are low entropy, right? They are not truly random strings, because you need to make, even for passwords, sometimes you need to make a message so that you can, meaning out of the password, right? So that you remember. Okay, so now what's the server? Okay, I mean, may not be directly related, but still, so now the server should authenticate, is this password right? So now it is going to compare with password file, as I mentioned before. Again, if an attacker steals the hard disk, your passwords are read and clear. So now store hash of passwords. Again, not just a hash, add some salt to it and then store it. So that's very quickly hash functions. So now what is an important bit that is left is public key crypto. So far we were discussing how to achieve confidentiality, encryption schemes, and then authentication, right? Using message authentication codes, and we saw primitives, PRS, PRGs to construct that. Even hash function is used to achieve message authentication, not just in the symmetric key setting, even in the public key setting. So let's go to public key cryptography. Everyone, do you know what is a Turing Award? It's like a Nobel Prize equivalent in cryptography. That's the in computer science. So yeah, this is the highest you can get. And what is the equivalent award in mathematics? Yeah, Fields Medal. So, and actually, do you know? Probably you would have heard of Donald Knuth, right? He's the only mathematician. No, even you can. It's not incorrect to say that the cryptographers are not mathematicians. You lose a lot of mathematical results. But so Knuth is like a kind of person with a purely mathematical background, and he's a great computer scientist. So he has won a mathematician has won Turing Award. But these are all cryptographers, and you know why they have got Turing Awards? They have all solved problems, very important problems. They have concerned with public key cryptography. Doesn't mean that symmetric key cryptography is less useful. It's extremely useful, and historically people were using that. So designing a symmetric key right from the Caesar's time, okay, they knew that it's possible. Oh, maybe, or I'm giving out too many details before the slides. Okay, now let's see why. So cryptography till the 80s, we saw some similar slides, but these are a bit different. So encryption schemes were all symmetric. Same key is used for both encryption and decryption. We have seen this a number of times already. But again, agreeing, if you have n parties, how many pairs you need? If you have n people, so there are a billion people, how many pairs of keys, or 7 billion people in the world? So how many keys you need? Is it n square? Okay, nc2, n choose 2, n into n minus 1 by 2. So key agreement is a problem. Earlier it was okay, because historically cryptography was used mainly for military applications. Governments could afford to do that. But now, in the internet age, everyone wants to talk to everyone else securely. That's not possible. So it was unthinkable. So this problem became a really serious problem. Key exchange, secure key exchange. And people believed that this cannot be done publicly. Key agreement cannot happen. That's what people believed. And of course, so let's look at the problem in more detail. So you should only use a public channel, you should shout, publicly shout, announce something. You are, even the recipient, both the parties, they should publicly shout, yet they should arrive at a secret that no one else can figure out, Actually, if you think about it, it's quite mysterious. So that's using a public channel, But you should come up with a key. Not too trivial. So how do you do that? Okay, yeah, people could not solve this problem. They believed, but again, so this is a workshop on school on theoretical foundations of computer science, right? We want proofs for everything. So, and no one proved either. It's not going to be possible. Like Shannon already showed that, if your key space is less than the message space, you can prove that, you cannot have a perfectly secure encryption scheme with decryption probability 1. So, but no one proved either. So then, so as the saying goes, God rewards fool. So this you see is Diffie, Whitfield Diffie. So he was investigating this key distribution problem. So in his notebook, he had an important entry called Problems for an Ambitious Theory of Cryptography. Remember, it was all in the 70s. So he visited IBM Watson Research Laboratory to give an invited talk about this topic. And he presented many, like tentative ideas, and the audience were skeptical, will this work or not? So then he came to know another Stanford professor, Martin Hellman, is also another fool working on the same problem. So then he traveled from the east coast to west coast, a long journey. And then they came up with what is called Diffie-Hellman key exchange. That's going to solve the key agreement problem. And that's changed many things. Have you heard of Diffie-Hellman before? Not those who have gone on a cryptographic course, others? Yeah, many, yes, okay. So, okay, asymmetry is present in the world, like, for example, you know that keys where the locks where you just press it, it will get locked, and you need a key to open that, you know that. So there is asymmetry, it's this asymmetry, meaning encrypting, locking something without a key and decoding is not totally a new concept. But again, opening without a key is extremely difficult. Not impossible, you can break it, but it's difficult, not as easy as locking it. Suppose you have two solutions, it's easy to mix them, and from the mixture it's not easy to, it's not as easy to get back the components. You can read for yourself. So again, to use the same solutions and the colors example, so suppose you have a common publicly known colors, and suppose you have some secret set of colors, this everyone knows you have this, this you say a secret to yourself, the green, the red and the green, you mix them, okay, you mix the publicly known color with the secret color and you exchange. Assume your solution satisfy this property. Assume, not always. Assume that if you add the blue with the red and this orange with the green, suppose you get dark green color. Assume it satisfies this property. So then you are exchanging, not the keys, something that is obtained by a publicly known information and a secret information that is truly private to yourself. Then you exchange something, and then you arrive at a common secret color. So to realize this one key mathematical ingredient that was required are one-way functions. Intuitively, we have seen in the hash function case, right? If you choose a random image, you should not be able to invert. We have seen that, this one-way function is also something very, very similar to that. So now, what's the algorithm? Okay, now we need to understand what are one-way functions. They form the basis for to get a key exchange. This is what Diffie did. They did not exactly formalize, all the theory again, just like the perfect secrecy thing. The construction came and then theory. If some construction is very, very useful, people would love to put in effort to understand, and then this formalism came. So, one-way functions, again, easy to compute, very similar to your hash function, but it's difficult to invert. This is one-way, as the name suggests. So, pick up a random y and then inverting, finding a pre-image is difficult. And many functions, like what is introduced to school or in our college, most functions, they are one way, squaring, over just real or complex numbers. Squaring easy, even extracting square roots is equally easy, right? Yeah, doing by hand may not be easy, but still, it's not impossible, right? It's not very hard. So, Diffie and Hellman, they worked for 2 years to find a one-way function. And this one-way function, as I mentioned, formed the basis of their key exchange scheme. So for that, we just need some basic math. Probably from school time, you are all familiar with modular arithmetic. So Z is the set of integers. Suppose you take 2 integers and let n be a positive integer bigger than 1. So then a mod n is just a remainder. In one of the second problem set, again you see the definition of mod. So it's just a remainder when divided by n. So when you divide by n, what are the possible set of remainders? Yeah. Good. So now just put all the remainders in a circle, So imagine a clock marked with 0 to n minus 1. So now suppose you want to compute a modulo of a mod n. So just go through the clock, say in the anti-clock, the clockwise, a number of times, and you hit upon a number which is basically nothing but a remainder. And yeah, that's how you ask the kids to compute the modular thing, the modulo, the remainder. So take n equal to 4, now 5. So you start with, you should start with 0, 1, 2, 3, 4, 5, and you get back 10. But in the modular world, functions can become quite erratic, not as predictable. We know this 2 power x function, f of x, say over real numbers, 2 power x is very nice, right? You can quickly compute 2 power x approximately. If it is a floating, x is a floating point number. Even the inverse can be, what is the inverse of 2 power x? The inverse function? Log. Log also with sufficient approximation, with a very good approximation you can compute, right? These are all easy. But the analog of this, the exponential function or the discrete analog, in the modular world we just have a finite set, right? Because everything, if it goes out of the set, pull it back by taking the remainder. So in the discrete world, this problem is, it's not as easy to understand it over the real case. And in cryptography, we almost always use finite sets. Even in computer science, like you can only handle finite quantities as of now, So now let's look at 2 power x. Again, now you define x over, okay, you can just define modular. You think that if you define x, say, over all positive integers or non-negative integers, so suppose you look at the table 2 power x mod n over all the integers, not just from 0 to 11, 0 to 10. So now suppose you make it over integers, you think the range is still going to be finite, or 2 power x, just take the function 2 power x, suppose if it takes all non-negative integers, so then your range is going to be finite or it's going to be infinite. Modulo n, it's not just 2 power x, it's 2 power x modulo 11. So ultimately you start getting repetition, right, eventually. Will you get repetition or it's going to become a random pattern even after 11 entries? My question is, okay, range is fine, but from a range, say, you can have like, say, even a bit strings, you can have infinite number of combinations, right, sequences, possible, distinct sequences. But here, 2 power x, after some point, it's going to repeat or not? Think, it's not a random sequence, okay. When you construct a random binary sequence, you always have a choice, right, the next bit. You can always choose it to be distinct, like to break the pattern. But here it's a fixed operation, right? Somewhere if it hits, because of the pigeonhole principle, because it's a finite set, okay, at most it can be 11 elements. After that, it's going to hit one and it's going to repeat, right? It has to repeat because it has to follow this table. In fact, it turns out that it's just exactly a permutation, 2 power x modulo 11. It's a permutation. I mean, so it's, you're going to repeat this sequence. In fact, it turns out that, if you take 2 power x modulo any n, if for x equal to n, you are going to get back, you will get back, how to say that? So g power x for a generator, okay, don't worry about that. But anyway, the pattern will only repeat, after some time. But here if you restrict the size from 0 to x, from 0 to 10, then you get a permutation. Look, this is no way seem to be related to the standard order, right, 0 to 10. And when can you use binary search? Only on an ordered set, right? So this is no longer ordered, you cannot use it binary search and or Newton-Raphson to get the compute logarithms. So here it's called a discrete logarithm. So suppose I give 8 and I ask you what is the discrete logarithm of what is the discrete logarithm of 8 modulo 11 with base 2? If 2 power 3 mod 11 is 8, then the logarithm, we define the logarithm of 8 with, we should define the base, right? And we are not doing it over real numbers, we are doing modulo, in the modulo world, right? So this is 3, so the pre-image is 3. If the modulo is not very well chosen, you can have repetitions, and then it's going to have many pre-images. But they are all equivalent logarithms. Now, they just use this idea, Diffie and Hellman. Take a prime, but this set behaves this sequence, if it is modulo p, then this is going to become somewhat nicely, it's going to become a permutation. So 11 is a prime, okay? So now we have, take the set. So by z star p, I mean the set of, by zp, I mean all the reminders, 0 to p minus 1. Zp means z subscript p. By z star, I mean you exclude the 0. Okay? This definition is only for primes, when you, in general, when you say z subscript n star, it has a different meaning, but it's a related meaning, but at least for the prime case, you can be sure that it's the set from 1 to p minus 1. Basically, Zn star is set of all the integers less than n, non-negative integers less than n that are relatively prime. And because prime, all the numbers from 1 to p minus 1, they are relatively prime to p, so that's why your z star p becomes that set. And one nice thing, if it is a prime, is any there are special elements called generators, What is a generator? Intuitively, it is generate a set. So here, okay, so in the previous case 2 was a generator, right? In that case, you see it's going to generate every element, but it can happen few for some base, say G or H. It can happen that you hit one quickly, and then it need not cover all the elements, it need not generate all the elements. So those elements that generate the set as like G power, powers of G, so then it's going to be, it's called a generator. And this was the candidate one-way function. Take a prime, large, very large prime, and then take a generator. If one knows some basic number theory, computing these generators is not too difficult, So if you choose a random, if P is a prime, if you choose a random element, then it's going to be with a good probability, need not necessarily be a generator, but with a good probability it's going to be a generator, and there are tests for that, Prime numbers, they have been studying from, ancient times, right? So all the mathematics has been developed, but yet the mathematics is not good enough to understand the property of this function G power X modulo the prime. Probably, even an equivalent hard problem is the factorization problem, and RSA is based on that. People have been studying, mathematicians have been studying factoring, but probably my understanding is probably mathematicians, they are more worried about the existence of prime factorization, but when the mathematics was diluted with applications, as in the terms of Hardy, so then people became more interested in the factorization problem. We know that every number has factors, but how efficiently you do it, So mathematicians did not give a lot of probably, or these things take time maybe. So they did not look at this sequence, given G power X modulo P, how to get back X. There is an X. If it is a prime, G is a generator, so G power X modulo P is just going to be a permutation of your set 0 to P minus 1. They all know, everything's proven, but how to compute it, it was not known, and people still don't know. Of course, there are better algorithms than the brute force algorithm, yet, you cannot efficiently compute X given G power X modulo P. And they just used it, So G, the prime can be made, the group, the prime can be made public, the generator, they can be made public, but then, but given G power X, it's difficult, the discrete log, computing the log, it's difficult. So this is a one-way function. No proof yet, no one knows, good enough for practice. So as I mentioned, X is called the discrete logarithm of Y to base G modulo the prime. So if P is 2048 bits, then it's going to be a hard problem, So your assignment, one of your questions in the problem set 3 are, okay, let's construct a different protocol, Let's not assume that G is known, assume the P is known, the X is known, okay, the Y is known, but now can you compute the generator? Is it hard? That's the question. So think about it. Again, if you cannot solve the general case, try out with examples, And one of the other questions in the problem set 3 is, I hope everyone can see here, but basically the first question says this, what are the last, suppose you take 3 power 10,000, and, okay, no, fine. So 3 power 10,000, what are the last two, and consider the decimal representation, the base 10 representation. What are the last two, the least two significant digits? What are the last two digits of, so that's one of your questions, And, okay, how do you do it? You would have done it in 12th, right? 10th or 12th, no?
10,000 divided by 3 and 31.
Sorry?
10,000 divided by 3.
Why that is the, why that should work? Why prove? Okay, prove it. Come on, at least use the hint, we are all talking about modular thing, so just take modulo, it's nothing but reminder. Okay, so what is the, say, 59, what is the last digit? 9, how it's related to 9 and 10? We are using decimal representation, means using base 10, right?
10,000 divided by 4.
10,000 divided by
4. We are asking
4.
Yes, sir. Because the repeating cycle.
No, see, last 2 digits, that value cannot be more than 100, right? It should be a 2-digit number, but 10,000 divided by 4 is 2,500. How can 2,500 be last 2 digits? It's 4 digits, right?
Then take the remainder, divide by 4. What is the remainder at last? Like, see, if it is 3 raised to 1, it will be 3. If it's 3 raised to 2, it will be 9.
Yes.
And 3 raised to 3, it is then 27, the last digit will be.
Yes.
So it's the same.
Not yet. No, it's not complete yet. No. Okay. Say 59. What is the last digit? 9. Okay, you know that because, okay, you can read the representation. You know 9, you can see that. But here you cannot write down, right? It's going to be a huge number, 3 power 10,000. So what is some way to compute? So 59, 10 power? Exactly, yeah. So 59, how you get 9? Just take the remainder and division by 10. So 243, what is, again, always try with simple examples, So 243, what is the last 2 digits? 43, how it's related? Just take the remainder and division by 100. And thanks to the modular thing, probably you all know, like, so computing 3 power 1000, so basically you just need to compute 3 power 10,000 modulo 100, right? What is the remainder? And you need not necessarily expand out 3 power 10,000 and then take it. The modular, every step you can always take remainder and your numbers will not go bounded, right? So the last digit is, okay, at least if we cannot do last 2 digits, at least what is this number modulo 10? 1. So basically your compute, so 3 square is congruent to -1, right? 3 square is congruent to -1 modulo. So if, okay, fine, okay, even if you don't know this, so take 3 power 4. 3 power 4 is 81, right? 3 power 4 is congruent to 1 modulo 10, right? If you know this, then this you can always get it as 3 square is congruent to -1 modulo 10, which is nothing but 3 power 4, 81. When you divide by 10 is going to remainder 1. And raise the whole thing, to 2,500, and 1 power 2,500 is 1. That's easy. The last digit is 1. So now how do you do it for 2 digits? Modulo, because when you say you take 3, 9, 81, 243, which is 40, you get 43. But then, it's not easy. 43 into 3 is 129. You got 29. Then you got 87. Okay, so this sequence is going to repeat or not? What if you want to try, you don't want to write down 10,000 times, right? The sequence. Will it going to repeat or not? Come on, we have already told the answer. Its modulo is just finite set, right? When you divide by 100, your numbers cannot be more, so you need to try at most 100 times. It's going to emerge, the pattern is going to emerge, right? So, actually it turns out you need not go far, 3, 9, 27, 81, 43, 29, 87, 61, 83, 49, 47, 41, 23, 69, 7, 21, and then it's going to repeat. So it turns out that 3 power 20 leaves remainder. You just need to go up to 20 and it's going to leave remainder 1. So 3 power 20 is 1. So raise it to 500 times 1. So answer is 1. And just check in case I have done a mistake. So easy, right? Good. So now we have a one-way function. Everything's good. So this discrete log is a one-way function. Now how do you do it? We have already seen this, the color example. So now, again, take a large prime, choose a generator, assume we can all find a generator. Everything's clear, This you can publicly announce, publicly shout, Both have the same thing. This is not a problem. This all information can be exchanged over public channel. Again, okay, due to time, I'm only talking about security against it's just I'm only worried about the privacy of the key. Still a man in the middle can intercept the communications. I'm not talking about message integrity or authentication. That's the next problem. Signatures, digital signatures handle that. But now I'm just worried only about the privacy, only the confidentiality. So when suppose Sita can send this to Rama, public channel, people will know this public information, but assume that no one can modify the messages. So then what you do is, both they pick up, they all know prime P, so they are going to pick up the two integers randomly, 0 to P minus 2, note that it's not P minus 1. So of course, both are going to pick up randomly, and it's with extremely high probability or probability close to 1, they are going to be distinct, right? They are not same. Good. Now, and then they compute, each compute quantity, which is just, they both know the generators, compute g power x modulo p. Modular exponentiation can be done, assume. You need not try, x can be very large, right? X can be of 2048 bits. How do you compute that? G power 1, G power 2, G power 3, or is there a clever way of doing it? Louder? No, I don't hear you. Fine. Binary? Okay, so it's called, what is a repeated squaring, right? Yeah. So it's repeated squaring. In a divide and conquer, you can just do it in, the log p many steps. If how many bits a prime number p or any number n, how many bits does it have in binary representation? Exact formula. Come on, undergrads, like if you want to face interviews later, you need to know all these things. Should be right on the top of the mind. It's logarithm of n to base 2 floor, round it off to the lowest integer and add 1 to it. So log p many bits approximately. So it actually needs only like something order of log p steps, if you do it cleverly using a recursion. So it's called repeated squaring. That's a very popular algorithm. So both compute these quantities, because they know x, they know g, they can all compute this. They exchange publicly. So now there comes the important property. We know that computing discrete logs is difficult, right? At least no one knows, Again, if you solve that, you are going to become famous. So g power x, g power y, computing the logs in the modulo p is difficult. They won't know x and y, So they just look like random messages, random log p bit strings. But then, magic, So okay, so Rama's thing, HR, Sita has received, Rama has received Sita's thing, but remember, they know y, and Rama knows y, and Sita knows x. Then just again exponentiate, and you get the secret exponent, which is g power xy. So idea is simple. Sita received g power x from Rama. Because it knows y, it can compute g power xy modulo p. Again, raise it to the g power x, raise it to the power y. You get g power xy. And the g power xy can also be computed from g power y, g power y. No, from g power x. Because it's, again, sorry, here you compute it as HR from Rama, g power y into x is g power xy. And again, here it is g power x into raised to the power y, is you get g power xy. This is easy, trivial. Again, it cannot, so your common key is going to be g power xy. Both cannot determine, remember, both cannot determine xy. Even Rama or Sita cannot determine xy. But it's enough, they use g power xy. The adversary cannot even compute g power xy, right? No one can compute x into y, that's granted. But your secret is not xy, it's going to be g power xy. modulo P. And the adversary cannot compute because at least, I mean, there's actually no proof of this, When people don't have a proof, why if you cannot compute g power x, the discrete log, why you cannot compute that? Still, that's an open problem. But like people have been trying for 40 years and they cannot compute it efficiently. So adversary also cannot compute g power xy, and so fine, Diffie. Then okay, they got this key exchange, Now they only arrived, but can you turn it into a public key crypto system, Okay, then what did Diffie-Hellman? They told you, they gave a proposal to method to compute the common secret and then use a symmetric key cipher. But they did not say, give a construction, how to design a public key encryption scheme, where you encrypt using a public key, but decrypt using a private key, Still, it's a hybrid approach, what Diffie-Hellman has solved. Share a key or a public channel and then use symmetric key. But then, so this is what, fine, okay, protocol 2. So before going to that, key exchange, actually it shocked the crypto community, brilliant, you can exchange secrets, fantastic. Not a perfect solution because it needs interaction, right? Both has to be online. I need to send, I need to receive secrets, some information. So both have to be online. But in a public key encryption, for example, in email, someone sends you an email and you look at it at your leisure, right? So we want something like public key actually is going to solve that. Encrypt using public key and I can decrypt whenever I want. But using this method, both the parties have to be online. So, and then they did not design public key cryptography, but then they gave a proposal. Okay, what if we can do that? So that's the public key thing. So they imagined, they just wrote a proposal, they did not give an explicit construction. They thought it will be nice if one design, and they, in the same breakthrough paper, they give, an imaginary encryption scheme that look like this. So person computes a private key, public key, two set of keys. One, he makes it public, put it in the public domain, and then and that message, the sender's message is encrypted using recipient's public key, because everyone knows the public key. Send it over a public channel, ciphertext, and then the recipient is going to put his or her secret key, uses his or her secret key, and then decrypt it. And then adversary looks only at the ciphertext, and it also knows the public key, right? It's publicly available. Yet it should not be able to find anything about the underlying message. So actually, if you can construct, then you don't need Diffie-Hellman key exchange. But here they could not do it. But later, one of his students, like 8 years, the Diffie-Hellman key exchange was solved in 1976. I think around 84, El Gamal, he just tweaked it, the Diffie-Hellman key exchange, to get a public key encryption scheme out of it. So it seems then Diffie remarked that we just missed it. So it was as easy as that. But okay, so for that you need to get a public key cryptography, you need what is called a trapdoor one-way permutation. Now we all understood what a one-way function is. Computing easy, reinverting easy, but to design an public key encryption scheme, you need what is called a trapdoor one-way permutation. So it's basically one-way function, a permutation. It's not just function, because when you get a ciphertext, you need to uniquely get back when you decrypt, you should get back the message, right? It has to be a permutation. In a Diffie-Hellman key exchange, you just had to arrive at one secret. You did not bother about inverting. But here, you want to decrypt a ciphertext to a message. So we just don't want a function, we want a one-way permutation. But it should also have, of course, it should satisfy the one-wayness, fine. But then, it should also have this trapdoor property. If you have some secret, which only you know, you should be able to invert. Means you will use that secret to decrypt. imagine such a function exists, you know. So then we readily get a public key encryption out of it, you know. Your function, F, one-way the trapdoor permutation, that itself is the public key. Like we know, we specified even in the Diffie-Hellman key exchange, the function is public, right? Everyone knows it's g power x modulo p. Given x, everyone can compute g power x modulo p on their own because it's publicly known. So that function here also is a public key, and the trapdoor is the secret key. So encryption is as easy as just apply the function. Everyone can do that. But to decrypt, to invert, you can invert. It's a permutation, right? You need the secret trapdoor. Escape. Ciphertext, secret key, and you get back message. And they all propose this, you know, no one knows. And they could not come up with a one-way trapdoor function. Of course, Elgamal made it much later. Before that, probably you all know, RSA people did it. Just in a year or two, they designed this. They basically designed this trapdoor one-way permutation. Of course, then all these terminologies were not known. Basically, this is all what you wanted, you know. You want a function that easy to compute, but with some secret information, you can invert back to decrypt. And oh, actually, this is Shamir, Rivest, and Adelman. And they patented it. They became very rich, and they got Turing Award for this. So, impact of the work of Diffie-Hellman key exchange. So now you get the key exchange. They solve the problem of key exchange, and then you need to use private key encryption scheme. In fact, surprisingly, even today, people use this hybrid approach. They use this Diffie-Hellman or maybe other methods to exchange the key, and then use crypto, private key, symmetric key crypto, because it's very, very fast. You know, all this modular exponentiation and your numbers are very big, right? But in your AES, you just handle 128 bits. You do many very simple operations, shift, rotate, you know, mix. Very, very, very efficient to implement. So, but of course, people use public key encryption scheme just for the, you know, to arrive at a secret key. What's the disadvantage of Diffie-Hellman key exchange? You need interaction, right? But now you can use public key encryption to just send the key. I choose the key. I encrypt using a public key, send it to you, decrypt, you arrive. So use of public key encryption, it can be made non-interactive. But again, you know, after that, once the session key is exchanged, then it's easy. Then it's going to be super quick. Excellent. So, and yeah, this was the original paper of Diffie-Hellman in Transactions on Information Theory, which is a very, very reputed journal. So the last we actually saw in the first lecture, there are many advanced applications of crypto other than secure communication and other than confidentiality and authentication, right? We looked at secure multi-party computation, digital cash very briefly, zero knowledge proofs, and homomorphic encryption, and then multi-party computation. But I just have only a couple of minutes, so I will only mention zero knowledge protocol because it may be used in the today's invited talk by Dr. Satyalokam. So it's simple. Suppose you know this, Ravana had taken Sita, and then Hanuman, he goes in search for Sita, but he takes something from Rama, a ring, so that so that Sita is convinced that Hanuman is a messenger of Rama. So then, fine, these are all okay. He takes the ring. Yeah, thanks to my colleague, he prepared a very wonderful set of slides. Fine, he says, goes to Sita, fine. So I have a message from Rama, but how to believe you? So then, what is that ring? Chudamani. Chudamani, right? What is the ring? What is the name of the ring? Okay. Okay, then Sita could recognize. I don't know, probably people had magical powers or not, they could not replicate, so that was enough. But it's not going to work here. People are pretty No, I don't want to make any comments, but in this Kali Yuga, it's not going to work. Or, okay, to put it more, politely and positively, people are more smart, they know how to replicate. So we want something crypto equivalent, So now the messenger should be able to authenticate himself. Like I gave an example, right? You solve the factorization problem. You don't want to give the proof, yet you want to convince some person that you know the proof without leaking the proof. So how the messenger should be able to authenticate himself without showing the credential in clear. So he cannot show the thing in clear. That's the problem, So they can do many interactions, play a challenge response game. They can exchange some communications without even showing the ring. They should be able to, Sita should be able to convince that Hanuman he knows he has the ring, He has the ring. He should be convinced without Hanuman showing the ring. And that's zero knowledge protocols. And this was designed by very popular cryptographer Shafiq Goldwasser, Micali, and Rakoff. It was published in STOCK. STOCK is one of the very popular, very top-rated conference in theoretical computer science. It was rejected in another, 3 times in other, FoCS STOCK. They are all. FoCS is another very top-rated conference in for theoretical computer science research. But then, okay, it got accepted. It became very, very famous. They got Gödel Prize for that. Tremendous applications, as you can imagine. I'll just couple of more minutes. I'll just give an example of how to construct a zero knowledge protocol for graph isomorphism. You all know graphs, right? Set of vertices, set of edges. But you can always redraw the graph in such a way that it looks really different. It's the same graph, and how. But we know equivalent. But how do you precisely tell what is these two graphs are equivalent? We need to put it precisely, right? In a mathematical way. It's nothing but there's a bijection between the set of vertices and the set of edges, such that the map, the bijection respects the edges. Suppose one, I don't know, like one gets mapped to A, 2 to G. So basically, like there should be a bijection, and it should respect the mapping should respect the set of edges. Means if there is a map between 1 to 5, and you look at the image, there has to be an edge there. So that's what it means. This bijection should satisfy this, respect this property. Trivial algorithm is run through all the possible bijections, check, whether this property is satisfied. If there is an edge, then even if you take the images, there should be an edge there. But this, how many permutations are possible on a set of n vertices? Yeah, n factorial, yes. No known polynomial. We don't want n factorial. It's exponential, right? But no polynomial time is known. But it's not even known to be NP complete. No. But still, can you solve this problem? Can I convince you? Suppose there are two graphs. Everyone knows publicly. Everyone knows G1, G2, but they just don't know this mapping. They don't know the mapping. I claim I know the mapping, but can I convince you without revealing the mapping? What is that map? Map is nothing but the bijection pi, right? So if I give you pi, you can verify very quickly. You yourself you can verify, right? Whether if there is this property is satisfied. That's easy. But you coming with that pi is difficult. But people have solved it. So what you do is you just pick up some random permutation. Let sigma be some permutation such that these two. This is the sigma that proves that G1, G2 are isomorphic. Just a minute or two. So then, so people are going to, the verifier is going to ask some questions, throw some challenges, get some response. At the end, he'll be, he'll be convinced, that I know sigma, may not be with 100% probability, but something very, very, very close to that. And that's good enough for practical purposes. And again, if I really know it, I should be able to convince the verifier that I know it. And of course, the verifier should be honest, right? If she simply says, no, I'm not convinced, you cannot do anything. And if the verifier is corrupt, he should not be able to know anything about the bijection. The procedure is extremely simple. Just take another random permutation pi. Now sigma is the one I have knowledge of, that is the secret. So pi, just take a random permutation, some random permutation, and construct a graph H out of this pi. Prover can always do that from G2. So H is just equivalent to G2. Still I have not proven that. I want to prove G1 is equivalent to G2. But here is just G2 equivalent to H. So then verifier is going to send a challenge. He's going to pick up either randomly I equal to 1 or I equal to 2. No, 1 at random. And then the challenge he's going to pose is show how to go from Gi to H. So Gi can be G1 or G2. So you randomly picked up a graph that is equivalent to G2. Then he is going to say that, of course, he will not say that, he will not necessarily say that show G2 is equivalent to H, There's no point. But now he is going to randomly pick up I, and he say it could be even G1, show G1 equivalent to H. It should be, right, transitive. If G1, G2, they are really equivalent, then composition of bijection will show that even G1 is equivalent to H, right? They are isomorphic to H, So then, okay, the response is if I equal to 2, that's easy, right? G2 showing equivalent isomorphic to H is easy. Give pi. Otherwise, mask your sigma with pi. Some permutation, just like a one-time pad. If a permutation is composed with a random permutation, the composition is also random. And then, so then that row, so if I equal to 2, he's going to send a row equal to pi or this. So then using that, he can always, verify whether that, even H is sent, right? So he can always check. And he knows which one he picked. He cannot cheat, there. So then using row you can, and row is a random permutation, It's not sigma. Yeah, so then it satisfies the correctness. If P prover knows sigma, he will be able to convince, and verifier will not be able to learn anything because what it sees is a random permutation. Okay, that concludes the lecture.